Hi, in this video I'll be discussing Chapter 5, Work, Energy, and Power. Starting off with work, in physics, work is a product of force and displacement. Displacement over here is denoted as S. Since this equation shows direct proportionality, if force and displacement are increased, work done will increase. If force and displacement are decreased, work will decrease. Based on the formula, what do you think is the unit for work? The unit for force is newtons, and the unit for displacement is meters. Multiplying them will give a newton meter, which is just equal to 1 joule. Therefore, the unit for work is joules. Now, when is work actually done? Work will only be done if the distance moved by an object is in the direction of the force, meaning that if force and displacement are perpendicular to each other, or at 90 degrees, there will be no work done. Most work will be done when force and displacement are parallel to each other. Moving on to energy. What do you think is a formula to find energy? Well, it's the same formula given to find the work done, because energy transferred is simply equivalent to the work done. When a satellite is orbiting the Earth, how much work is done? Actually, it's 0. No work is done since displacement is 0. Displacement is 0 because the satellite completes a circle, reaching the same point it started at. In this example, however, work is done since the man is able to push his car in the direction of the force. Let's say that he supplies 300 newtons, and the distance his car moves is 5 meters. Multiplying these values together would give 1,500 joules. Now, how would we find the work done if the displacement is at an angle to the force? This is when we can use sine, cosine, or tangent. Let's take a look at this example. We need to find the work done by each force on the box. Let's start with this upward force. Simply multiply 100 newtons to the distance moved, which is 0.5 meters. Next, how about this force? Remember we said that if the displacement is perpendicular to the force, work done will be 0. The boxes move parallel to the slope and perpendicular to the 70 Newton normal force. Next, this force is going in the negative direction. So negative 30 newtons times 0.5 meters will give negative 15 joules. Lastly, how about this force? Let's draw a free body diagram to understand this. Take note that theta is equal to the angle given, which is 45 degrees. Let's rotate this diagram. We can get this angle in blue by subtracting 45 degrees from 90 degrees, which is the right angle. Let's take a closer look at this triangle. We want to find the force at this dashed line. So labeling the adjacent and the hypotenuse sides, we can see that cosine 45 degrees is equal to adjacent over hypotenuse. Hypotenuse is negative 100 newtons. Cross-multiplying, we can find the force at adjacent, the dashed line. Now we have force, which can finally be multiplied to the displacement, 0.5 meters, giving us the work done. Did you know that work done on a gas can also be determined? This is the formula to find that. How do you think this formula was deduced? Well, first, let's imagine a piston as shown in the picture. Force is exerted by the piston on the gas, and S is the distance the piston moves to compress the gas. The cross-sectional area is denoted as A. Starting with the formula for work, F can be replaced with pressure times area according to the formula for finding pressure. That leaves us with pressure times area times distance. Area times displacement is a change in volume, thus leaving us with pressure times the change in volume. Now, let's move on to the different forms of energy. Gravitational potential energy, or GPE for short, has the formula mgh. mg, or weight, is a force. This force is multiplied by height, which is a form of distance. Thus, we come back to the same force times distance equation. Therefore, mgh is also work done. However, this is only useful when an object is at a certain height above the Earth. Let's look at this weightlifter. We want to know how much energy he is transferring to the object when he lifts it. Since the object is at a certain height of 1.5 meters above the Earth's surface, we can use mgh. Let's assume the object and his mass is 200 kilograms altogether. We get the answer of around 2940 joules. Another form of energy is kinetic energy. The formula for kinetic energy is 1/2 mv squared, where m is the mass and v is speed. How do you think this formula was made? Let's try to imagine a car being accelerated from rest. This means initial velocity u is 0. Using one of the 4 kinematics equations, v squared is equal to u squared plus 2as, we can remove u since it is 0. Now we have v squared is equal to 2as. Multiply both sides with 1/2 m. Now we have 1/2 mv squared is equal to mas. F is equal to ma. Thus, that becomes F times S, work. To find the change in kinetic energy, simply minus the initial kinetic energy from the final kinetic energy. In this problem, we need to find the kinetic energy of an 800 kilogram car that has an initial speed of 20 meters per second and a final speed of 30 meters per second. First, find the initial kinetic energy using 20 meters per second as v. Next, find the final kinetic energy using 30 meters per second as v. Minus the initial kinetic energy from the final kinetic energy, and now you have the change in kinetic energy. Since 1/2 mv squared is self-explanatory when using it in basic problems, let's take a look at some energy changes. Energy changes mainly occur when GPE decreases and kinetic energy increases, and vice versa. This roller coaster is a perfect example of a problem that includes energy changes. You can see that GPE is highest at the maximum height and lowest when at the lowest height. Kinetic energy is the highest when the cart moves fastest, and GPE is being transformed into kinetic energy as the cart falls from maximum height, speeding up the cart. Taking a look at this 5 kilogram pendulum, we can show how to get V without the use of the square root of 2gh. The gain in kinetic energy is the loss of GPE, and vice versa. We can equate potential energy and kinetic energy as mgh is equal to 1/2 mv squared. Solving for mgh, we get 7.36 joules, which is then equated to kinetic energy. V is isolated and the speed is around 1.7 meters per second. Note that this could have been solved with V is equal to the square root of 2gh. However, we did this to show how energy changes work, or to prove that energy changes work. Many objects don't use their energy or transfer it 100%. To find out how efficiently energy is being used up, the following formula can be used. This has something to do with the conservation of energy. The law of the conservation of energy states that no energy is created or destroyed. Energy can only change in form. A Sankey diagram shows this. Here's a car's Sankey diagram. The thick arrow shows energy lost to the environment, while the thin arrow shows energy used up. Energy is not appearing out of nowhere, nor is it being added randomly. In this problem, we see a dam with an outlet 20 meters below its top surface, where water is leaving that outlet at 16 meters per second. We're asked to calculate the percentage of the GPE that is lost when converted to kinetic energy. Since no mass is given, we will use 1 kilogram of water. Our goal here is to get the GPE lost, so to do that we need to do mgh minus 1/2 mv squared. So that would be 196 joules minus 128 joules all over the GPE we calculated. Therefore, 68 over 196 times 100 gives 35% energy loss. Lastly, let's talk about power. Power is the work done per unit time, meaning it is also the energy transferred per unit time. The unit for work or energy is joules, and the unit for time is seconds, giving us joules over seconds, which is basically 1 watt, the unit for power. To deduce the formula for power, starting with the equation for work, displacement can be replaced with velocity times time according to the formula for finding displacement. This becomes F times V times T. FVT is work, so let's equate that to work. Now FVT over time is also work over time, which is basically power. Simplify the equation and we get a new formula to find power, force times velocity. So these two formulas listed here, work over time and force times velocity, can both be used to find power. Again, we see that the unit for power here is watt, as the units for force and velocity give Newton meter per second when multiplied. Let's say that one of these elevators starts moving from rest with a speed of 5 meters per second going upward. It takes 30 seconds for the 1,100 kilogram elevator to reach the top floor. How much power does the elevator have in order to reach the top floor? Power is work over time, or energy over time. Since we are given speed, we can use kinetic energy over time. To be specific, we can do the change in kinetic energy divided by the time taken. That's because we're given initial and final velocity. So final kinetic energy is 13,750 joules, and initial kinetic energy is 0 because initial speed is 0 since the elevator started moving from rest. 13,750 joules all over 30 seconds gives us power, around 458 watts. And that was it for this lesson. Thanks for watching. Bye!